Hello students, welcome to lecture 12. In this lecture we're going to talk about the shape of the graph. So we'd like to figure out what affects the shapes of the graph, and the first topic of the discussion is when the function would increase and where the function would decrease. Alright, so the terms increasing, decreasing, and constant we're going to use to describe the behavior of a function as we travel from left to right. Along the graph. So let's quickly look at the example. Suppose we have a function that looks something like this. So we can clearly see that up to this point the function is decreasing. Right, decreasing. So let me write it. So in this region the function is decreasing. Why? Because if we move from left to right, our function is going down. And in this region over here, the function is increasing. Why? Because while we're moving along the graph, we're moving up. And in this region over here, it's constant. So we're moving from left to right, and we're moving along the graph. We're moving along the graph. So can we do it a little bit more precise, because this was just a lot of hand waving? Definitely we can create a definition of the increasing, decreasing, and constant parts of the graph. So let f be defined on an interval, and let x sub 1 and x sub 2 denote 2 points on the graph. Right, so, and these 2 points are in the interval. So first definition that we can make is f is increasing on the interval if f of x1 is smaller than f of x2 whenever x1 is smaller than x2. So picture-wise, we have something like this. We have an increasing function, and if we take x1 on the left side of x2, right, then this height, which is f of x1, and this height, which is f of x2, so f of x2 is bigger than f of x1. So second part of the definition would be f is decreasing. So we say f is decreasing on the interval if f of x1 is bigger than f of x2 whenever x1 is smaller than x2. So picture-wise, we have something like this. The function is decreasing, so if we pick x1 to be here and x2 to be here, this height f of x2 is smaller than this height f of x1. So basically this distance is bigger than this distance. All right. So last part of the definition, part 3, says that f is constant. Constant means does not change, right? F is constant on the interval if f of x1 is equal to f of x2 for all points x1 and x2. So visually we have something like this. We have a constant function, so whenever you take x1 and whenever you take x2, f of x1 is the same as f of x2 because this distance over here is exactly the same as this distance over here. Right? So we got these two definitions, three definitions, sorry. So basically, let's look on the connection to the derivative. What is the connection to the derivative? So let's look at the first case. If we have an increasing function, then if we try to plot few tangent lines, we will see that all tangent lines have a positive slope, right? So each tangent line has a positive slope in this case, right? So second situation that we had was a decreasing function. So if we have a decreasing function and if we draw tangent lines, we'll see that all tangent lines have a negative slope, right? All tangent lines have negative slope. So each tangent line has a negative slope. And the last situation to discuss is a constant function. So if we draw a constant, then each tangent line, if we try to draw it, it will match up the function itself. So conclusion, the slope is 0. So we can say that each tangent line has a 0 slope. Has 0 slope, right? So let's try to put it as a rule, right? So theorem to discuss this situation. Okay, so let f be a function that is continuous on a closed interval AB and differentiable on an open interval AB. Then part 1 of the rule says, if f prime of x is greater than 0 for every value of x in AB, then f is increasing on AB. Second part of the rule says, so this is our first picture. So picture 1. Right, this is picture 2 and this is picture 3. So second says that if f prime of x is negative for every value of x in AB, then f is decreasing on AB. And this is picture 2. And the last part of the rule says, if f prime of x is equal to 0 for every value of x in AB, then f is constant on AB. And this would be picture 3. All right, so, and last thing to talk about this theorem is some note. So our note is, although we stated the theorem for closed intervals, it would also work for the open intervals, for any interval for which, maybe on which f is continuous. So for example, if f is continuous on e to infinity and f prime of x is greater than 0 on a to infinity, then f is increasing on a to infinity. And if f is continuous on negative infinity to infinity, and f prime of x is negative on negative infinity to infinity, then f is decreasing on negative infinity to infinity, and so on. So we haven't done any examples in this small lecture, but we'll do a few examples in the next lecture. I'll see you next time.